Right, so the rest of the slides are pretty easy in this chapter. What the slide is saying is that, basically a summary, the goal of an action potential is to release neurotransmitters. So here are the steps at the end. An action potential goes down to the ends, calcium first enters, and then calcium. An action potential is an all or none response, meaning if the depolarization is not strong enough, if it is too weak, then no action potential occurs. So remember, just like dominoes falling, if you can make the first domino fall, then you can make the other ones fall. So if you can open up those first voltage gated channels, you can open the next ones. During the time of action potential, there are these time periods, refractory periods. I'm going to show you on the next slide on the graph. But here, there's this time period during an action potential called the absolute refractory period. During this time, the neuron cannot generate another action potential because the first one hasn't ended yet. Then after the absolute refractory period, there's the relative refractory period that follows it. During this time, a new action potential can be generated, but a stronger stimulus is needed to generate another action potential. So if you look on the slide, the absolute refractory period is during this time. Here, the neuron hasn't finished doing its first action potential yet. The sodium channels are kind of still open. But after that, relative refractory period, here we can generate another action potential, but it has to be stronger than normal because here the neuron is dropping down to the negative. So it's almost like free falling. So you have to get stronger depolarization to do another action potential. So we learned that myelin covers the axons. Myelin sheath is made by the Schwann cells in the peripheral nervous system, oligodendrocytes in the central nervous system. Myelin is rich in lipids, and it prevents the crossing of ions. And if you remember, there are those gaps in the myelin sheath. Those are called the nodes of Ranvier. So only in these locations, only on the nodes of Ranvier, is where the voltage-gated channels are located. You cannot have voltage-gated channels where you have the myelin sheath because the myelin sheath is covering those parts of the axon. So only the nodes of Ranvier have these channels. So on the next slide, it's just going to show you what saltatory conduction refers to, but it refers to how the sodium channels are opening in these nodes around here. And I also wanted to point out here, axon diameter, meaning the width of the axon, can influence the speed of an action potential. So if the axon is thick, and if it also has myelin, then the action potential is going to be much faster. But if the axon is thin, meaning narrow, and it's unmyelinated, and so here we're seeing the action potential much slower. So here on the slide, we're seeing the myelin sheath covering the axon, and the gaps are called the nodes of Ranvier. And so this is where you have the voltage-gated channels. The sodium ions come in. So the sodium ions are traveling inside the axon, and then more sodium comes in. So then again, travels inside, more sodium comes in. And so they thought that this looked like jumping from one node to the next. Okay, excitatory postsynaptic potential versus the inhibitory. So these just really refer to, excitatory would be depolarization, when those ligand-gated channels open on the dendrites in the cell body and sodium enters. And so here, depolarization leads to action potentials. And so this is just a different type of the graded potential, the depolarization type of graded potential. And the inhibitory postsynaptic potential, so here instead you bring in negative charges or make the inside more negative. And so the other word for this is hyperpolarization. And so here either potassium channels could open on the dendrites in the cell body, then potassium leaves. When it leaves, it makes the inside more negative, or chlorine enters the neuron. Okay, so if you make the inside more negative, this reduces the chance for an action potential. Okay, and so this is just showing that inhibitory postsynaptic potential. So it's just saying that if chlorine comes in, it makes the inside more negative in the dendrites in the cell body, while making the inside more negative then reduces the chance for an action potential. Only if it becomes positive inside, it leads to an action potential. Now, what can happen is here's a summation of EPSVs and IPSVs. It could happen that one neuron causes the EPSVs, or the excitatory postsynaptic potential, and the other one causes an inhibitory. So let's say that this top upper presynaptic neuron releases acetylcholine. This leads to sodium entry. But let's say the other one releases serotonin or GABA. This opens up chlorine channels instead. So here, the positive and the negative charges are battling each other. So whichever one you brought more of, if you brought more of sodium, more positive charges, then the positive charges would win out. But if you brought in more chlorine charges or negative charges, then the negatives would win out. But yes, this is called summation. Now you might be thinking, why do you want to make the inside more negative? So why would serotonin or this other neurotransmitter GABA cause the inside to become more negative? This is more about controlling. So those neurotransmitters are for controlling emotions, also controlling appetite. So I'm going to show you on the table about the different effects of those neurotransmitters. But it's for moods and behaviors and satiety. And so here, this table is showing the different neurotransmitters. Now there are 100 neurotransmitters, but these are the ones that that we see more. So acetylcholine leads to sodium channels opening. But if we look here, serotonin it says inhibitory. Yeah, so this leads to sleepiness, saying actions blocked by LSD, which is interesting. Serotonin reuptake inhibitors are used as the antidepressant drugs. Here's another one, GABA. So this one's also inhibitory. So this one is also controlling moods. But yeah, so the neurotransmitters that allow negative charges to come in are just for controlling the behaviors and moods. Yeah, so then this table is just showing different disorders associated with neurotransmitter imbalances. You can read that on your own. There, I won't ask questions on these. And some more drugs here that alter neurotransmitter release. Opiate drugs, morphine, heroin, codeine, opium. So these are painkillers. Our body actually makes natural opiates. So these are called endorphins. So yeah, in our body, just naturally released, they relieve pain. But also we have seen that acupuncture can lead to the opiates to get released in our body during exercise as well. But unfortunately, with drugs like morphine, heroin, codeine, they lead to withdrawal symptoms. So what is happening is the person gets used to the dosage and it's just not enough. So then the person starts taking more and more and more until it can lead to the end of breathing. Okay, neuronal pools. This just means that more than one neuron contacts other neurons. Yeah, so in that video with the action potential video, we also saw this. There's just many neurons contacting each other. So here's one, here's another one, here's another one. And so here, those three neurons are contacting this neuron. But of course, it's many more. So what this helps us leads to facilitation. So if you have more neurons, then you have more neurotransmitter release, repeated stimulation of the neurons. Convergence means that one neuron receives input from several neurons. So here, two neurons have converged onto this neuron. And so they're releasing their neurotransmitters onto that one. And a divergence means one neuron contacts more than one. Okay, so again, these pictures are very simplistic. You have so many neurons contacting each other, but know the difference between convergence and divergence. Okay, and then our book talks about drug addiction. I suggest that you read this section in your book on drug addiction. Know the difference between antagonist and an agonist. Okay, well that's it for this chapter.